Hello there, Mr. Sutton here, bringing you this lesson on polar functions advanced area. In this one, we are going to be finding area between curves of polar functions with multiple functions and also involving some tricky limits of integration. We're going to start this one right up with an example. Here we're trying to set up but not evaluate an integral that gives us the area inside this three-petaled rose described by this function here. Now this is a no calculator problem, but to show you why this is in the tricky area section, I'm going to actually cheat and use the calculator. So here's my function in r equals in polar mode, and I've already got my window set to 0 to 2 pi, so let me zoom 0 this thing and see what this looks like on a graph. And big shock, it looks exactly like the one I drew here. But here's the important part. Let me trace this thing. So I'm starting at the angle 0, and that it's hard to see, but I'm right over here at the very edge here. Now as I keep cycling through my angles, you can follow my little spider as he goes around this rose here. And you see that it takes us, let's see, how long did it take us to get back to where we started and get all the area? Well, we're at pi, not 2 pi. 2 pi is normally what you would think of as the whole cycle, but this only took us a distance of pi. So if you keep going around, like if you took an integral from 0 to 2 pi instead of pi, well, then you're getting all of that area one more time. You're double counting. And we're not really going around in an intuitive fashion either. So because of that, and to avoid double counting, it's safer to just find the area of a smaller repeated piece, like just one of these petals, and then multiply by the number of pieces. So that's how we're going to do this particular problem. So with that in mind, pause the video, see if you can find the area of one petal. Probably this one's going to be the easiest, and then use that to find this total area. All right, so to find this first petal, because I'm going through the poles here, I'm going to set my r value, 2 cosine 3 theta, equal to 0 and solve. So I can say then that cosine of 3 theta equals 0 if I divide by 2, and then I'm going to inverse cosine, so 3 theta equals, well, whatever angle we get an x value of 0 out of on the unit circle. Inverse cosine of 0. Where is cosine 0 on the unit circle? Anywhere x is 0. Anywhere on the y-axis. So that would be angles like pi over 2, 3 pi over 2, 5 pi over 2. And I'm going to include negative pi over 2 down here because I really do want to get this angle that's a little bit below the x-axis. So I'm going to say 3 theta equals negative pi over 2, and I don't have to list out the infinite answers. These are going to be good enough. Dividing by 3, I've got negative pi over 6, and I have to go through all these motions because this is a no calculator problem. So now I've got the limits of integration. I've got the r value for taking an area. Let me find my three-petal area now. So that's going to be 3 times an integral from negative pi over 6 to pi over 6. That's going to give us this right here. And then I have 1/2 r squared d theta, so 1/2 all of this stuff squared d theta. And there's my setup. I could call it a day if this were a free response problem. But these are often multiple choice, so if I needed to simplify this, one thing I could do is square all this stuff and then multiply by 1/2. So that would be 4 cosine squared of 3 theta times 1/2. Well, that would be a 2, and then 2 times the 3 out here would give me a 6. So 6, and then same integral, all that stuff, negative to positive pi over 6, cosine squared of 3 theta d theta. So this is probably what the answer choice would look like on multiple choice. Now another way to calculate this area, instead of taking a whole petal, maybe you didn't want to mess with this negative pi over 6. Maybe that weirded you out a little bit. So you could have actually done a half petal, just this half petal in the first quadrant, and multiplied that by 6. So let's say we had 6 half petals. Well, then your limits of integration would be from 0, where the first quadrant starts, to this would be, let's see, pi over 6. We found that earlier. Everything else would be the same at the end of the day inside, but because you have twice as many of these half petals, on the outside you'd end up with twice whatever this was, so that would be a 12. Now in general, this is a safer way to do things, either a half or a whole petal. Also, multiple choice setup only answers are usually expressed with repeated area, so you just won't get the answer you're looking for if you don't use this method on these kind of symmetry problems. For this next example, it's a calculator one, and they want the area shared by the circles given here, Pause the video and graph this out and see what they're really looking for. So here are my functions in R1 and R2. Let me zoom fit this thing. I'm still going from 0 to 2 pi. So there's the first circle, there's the second circle. Let me just draw it out on the screen here. So we're looking for this shared area in here. So how do I find this? Well, one thing I'm going to need here is this angle of intersection, and possibly this one as well, because this area is basically the radius of the r equals 2 sine of theta circle up until we get to this point. And then this r equals 1 circle, the radius strips from that are going to take over. That's what we care about. But then we have to switch back to this other circle once we get to this spot right here. So how do we find those intersections? Well, you can't do it in polar mode. For multiple functions, you're going to have to find angles of intersection, just like we said, and you're going to have to do that in function y equals mode. So basically graph y equals 1 and y equals 2 sine of x. Pause the video and find the first intersection. So here I am back on my calculator. As you see here in mode, I'm switching back to function mode. Now I'm going to go to y equals and enter these off camera. There we are. And let me also set my window to make sure I'm going from 0 to 2 pi because that's the interval I care about here. Zoom fit. And let's see what our graph looks like. All right, so there is our first circle. There's our second circle. Now we're just graphing the radius here as a function of the angle. And I just need this first intersection for now. That's corresponding to this intersection on the polar mode. So let me do second trace, option 5. And I'm pretty close to that. Let me just move my spider over there. So enter 3 times. And we end up with about 0.5236. So there's my setup. I'm setting these equal to each other. I found my intersection. And I'm going to actually set it equal to Q just so I can use that again as needed. So let me escape out of there. And I'll do store alpha Q. There we go. All right, so now what? So now to find my area, I'm going to have an integral, an area integral, just taking the area of this top circle, 2 sine of theta, up until point Q. But then I'm going to need another integral that takes over and uses the r equals 1 circle all the way from Q to whatever this point is. But then we're going to have to switch again. So that's going to be kind of annoying because I'm going to have 3 different integrals. If you want to get around that, a strategy on this, using kind of what we did on the last problem, we noticed that this shared area is actually symmetrical over the y-axis. So you could think of this as not 1 but 2 areas, both of which are identical. What if we just found the area of this quadrant 1 spot here, and then just multiplied that by 2? That would completely avoid the issue of having to switch our limits of integration again. So that's what we're going to do. Pause the video and see if you can get the setup with the integrals for making that happen. All right, so my area for my first integral, I have the integral from 0 to Q. That's taking me from here to here. And that's going to be the 2 sine of theta that I'm squaring and taking half of with the d theta. Next to that, I'm going to add an integral from Q until pi over 2, because I'm just staying in the first quadrant with this strategy here. And that's going to use this 1 here, so 1/2 1 squared d theta. And at this point, I can just plug it in my calculator. And this is going to give me just the quadrant 1 area. So here's what I've entered for this first integral. I've got integral from 0 to Q, 1/2, and I stored this 2 sine of theta 1 in y2 in function mode, so 1/2 y2 squared dx. Let me get the other integral now. So here's my other integral from Q to pi over 2, 1/2, and I was a little silly here. I've stored 1 as y1, so I did y1 instead of just writing 1. It's the same thing. And then square that dx, and all of that gives me a grand total of about this, 0.6142. So I'm going to store that as the value a because I'm about to use that. So let me just store that as alpha a. So how am I going to use a? Well, I just found half the area I actually needed. So to get the real area, I just need to multiply that by 2. So let me go back here. 2 alpha a gives me my true area of 1.228. We'll do one more example. Pause the video and graph out this situation. We want the area inside the circle r equals 2 and outside this cardioid. So here are those functions in my R equals. Zoom fit gives me first the circle, then the cardioid. So let me draw that out here. So we want the area, they said, inside the circle, outside the cardioid. So that's this area here in this top little region. Okay, how do we find this area? So there's a few different ways to do this, but one thing I do notice, if I want the area that's inside the circle but outside the cardioid, half of the circle down here below the x-axis doesn't even belong in our answer because it's all inside the cardioid. And then we have most of the top half of the circle we do want to keep. We just don't want these little pieces here that are part of the cardioid. So my strategy on this one, and there's a lot of ways to do it, I wanted to basically subtract this little piece of the cardioid from the upper semicircle. So you have this area in the semicircle that you're going to find, and then you just want to carve out these tiny little pieces of the cardioid. So that's what I'm going to do algebraically with some integrals. And one other thing you can keep in mind as you're doing this, because you're probably going to start finding the area of this circle here, if you just have a regular circle, for circle and semicircle area, it is possible to just use regular geometry. I mean, you don't need to use an integral to find the area of a circle. You already know how to do that. So pause the video and see if you can come up with the setup for this. All right, so for my semicircle area, this is what I'm talking about with geometry. I have a circle with a radius of 2. I just want half of it. So let me just do 1/2 times pi times 2 squared. There you go. No need for an integral there. Now, I also need to subtract this cardioid area. So I need to subtract an integral from, this will be 0 to pi if you trace the cardioid on the calculator. And you can. I mean, let's go ahead and do it now. So here we go. Let me do trace, and you can see up here in the upper left it tells you which function you're on. If you press up or down, it'll put you on the other function. So now I'm on my cardioid, and it looks like I'm at angle 0 right there. As I move along my angles, that's exactly the direction I thought I was going, counterclockwise. And this other spot here is pi. So that confirms we want an integral from 0 to pi. We're going to be subtracting it. And that's just going to be 1/2 times your cardioid r squared d theta. And it's calculator time. So here's what I've got on the calculator. This is my semicircle area, and here's my integral I'm subtracting. And I stored my cardioid radius as r2. So pressing enter, that gives us about 4.858. There we are. So that'll just about do it for polar area. I mean, we could keep going, but I don't think my cardioid could take any more of this. Till next time, Mr. Sutton signing off.